RDT 2.2. It's essentially the same as 2.1 except here. It's going to be the NAC-free version of 2.1. By saying that, what I meant is, well, in 2.1, when the packet arrives at the receiver, okay, we send positive acknowledgement, that is ACK. Well, in case that data packet is corrupted, we send a negative acknowledgement, that is NAK. Now, as a result, we do have like two packet formats, right? One says I am acknowledgement, the other says I'm negative acknowledgement. So RDT 2.2 here is essentially to say, let's not have two different packet formats, just have one acknowledgement packet, but adds a bit in the acknowledgement packet, and we change the bit, okay, the value in the bit to indicate whether it's really a positive acknowledgement or a negative acknowledgement. All right. So same functionality as 2.1, but using only ACK packet. But the ACK packet will be carrying an extra bit. That is also the sequence number. Okay, so that is the sequence number bit. Okay, and the value in the sequence number bit is going to tell the sender whether this is a positive acknowledgement or a negative acknowledgement. All right. So now we have, a NAC-free protocol. Receiver sends acknowledgement packet for the last packet received. Okay. Think a little bit about it. So the receiver starting from waiting for call from below 0, right? So if packet 0 is received okay, receiver here sends acknowledgement for packet 0. Because packet 0 received okay. The last packet received okay is what? Sequence number equals 0. Now, go to wait for call from below, packet 1. So if packet 1 arrives at the receiver and it's corrupted, what does receiver do? Which packet is the last received being okay? Well, 1 is not okay. So, still sending ACK packet, but sequence number bit there is 0 again. All right. But at the sender side, what's going to happen is sender will receive the first ACK with sequence number 0, right? Indicating packet 0 is received okay. But sender there is going to receive another sequence number 0 ACK. Ooh. Hey, how come I get acknowledgement for sequence number 0 twice? Yeah, having duplicate acknowledgement at a particular sequence number that indicates the next data packet that sender just sent out was corrupted. A negative acknowledgement in a way. So receiving duplicate is essentially signaling, sender is sending a NAC, all right? So sender there will have to what? Retransmit the packet that's last sent. Now let's try to develop RDT 2.2's finite state machines. So here what we will do is to borrow from 2.1 and start from the receiver side of the finite state machine. All right, so initial state is wait for 0 from below. So we're expecting data 0. And we get 1 if it's not corrupted and indeed carrying sequence number 0. Then we extract data, pass it up to the application layer, generate an ACK packet with the checksum, and then send it out. Now, if it's 2.2, we'll be generating an ACK packet, all right, but this ACK packet should be carrying a sequence number, isn't it? And according to 2.2, the sequence number should be the last data packet received okay. And what is the sequence number of the data packet received okay? Well, we just actually received 0. So, you're correct. The ACK packet we're generating here for RDT 2.2 should carry sequence number 0. And so once we finish all the actions, we'll be finishing the transition and move to the next state, wait for 1 from below. And if we get packet 1 coming in, passing these conditions, so indeed carrying sequence number 1 in this data packet, then similarly, we take the data out, generate ACK, and send it out. And here, the ACK sequence number will be what? Yeah, data 1, the sequence number that we just received. So as a result, we could actually conclude the receiver side of RDT 2.2 should look more like this. And I'm ignoring the upper right part of the receiver's finite machine. So, receiving a packet, not corrupted, carrying sequence number 1. The ACK packet will be generating, of course, it needs to be an ACK packet format, carrying checksum. It also carries what? The sequence number of the data we just received, okay, and which is 1 here. So for this other transition at the top, then it will be make packet 0 ACK checksum. Now, hey, the receiver side of RDT 2.1 actually have all these other transitions, right? So we only handle this part and extend it to 2.2. We will still have to extend these transitions so that it will work for 2.2. Now, these are actually exact mirror of each other, so let's just focus on one side. Okay. Now, let's pick this transition first and see if we could evolve it as well into 2.2. So this is receiving a data packet, but it's corrupted. So in 2.1, we send a negative acknowledgement. But for 2.2, we don't send negative acknowledgement packets anymore because we don't have that format. Instead, we send ACK. But we have to carry a specific sequence number to indicate whether this is really a positive acknowledgement or a negative acknowledgement. So, yeah, the rule of thumb generating the sequence number there is what? Who is the last data packet received? Okay. Now, receiver is currently waiting for data 0 coming from below. So what that means is that the last packet received OK should be carrying sequence number 1. So ACK here should give the sequence number of the data packet last received OK. So yep, it should be ACK1 here that we're sending back to the data center. Now, what about this other transition? Receiving a packet, not corrupted, but carrying sequence number 1. This is not the data 0 we're expecting. All right. How can this be happening? Yeah, so this is the very odd situation where the previous data, ACK, being sent back to the sender gets corrupted, if you recall. Yeah, ACK packet or negative acknowledgements can be corrupted now, right, in version 2. Now, if negative acknowledgement is corrupted, sender simply retransmit, no problem. But if positive acknowledgement gets corrupted, sender also retransmit. And that is this situation here. You already sent back an acknowledgement for data 1, and yet it's receiving data 1 again. Yep. So this is the situation. ACK packet gets corrupted, and so you're receiving a duplicate of data 1. So we do not extract data and pass it up to the application because that's going to repeat words, repeat letters, repeat sentences. Okay. So we only send back ACK. And this ACK should be what? Acting the last packet received OK, therefore also carrying sequence number 1. Okay. Now, if you look at this guy and this guy, both transitions, the actions they'll be taking will be identical now, right? Both sending acknowledgement packets carrying sequence number 1. So then perhaps we could just combine the two transitions. Receive a packet from below, checking if it's corrupted, or carrying sequence number 1, send ACK packet 1. Right? And you know what? ACK packet sequence number 1 is already being generated here. Send PKT, if you do not replace this variable's value, it will remain the same. And so if we just simply call this, then, yeah, we just combine the two transitions and make it very brief, like this. RDT, either corrupt or carrying sequence number 1, simply send back the send packet that has been generated here, which is an ACK with sequence number 1. Now let's try to develop the sender's finite state machine. Again, let's borrow 2.1's sender finite state machine and start from there. This is the initial state. We wait for call from above. And if there is 1, then we generate starting from packet 0. And then we enter that wait for ACK state. Now in case a NAC is in, we do have this is NAC check, isn't it? Okay. So if that is the case, we retransmit the data. Otherwise, everything is fine, and this is a positive ACK, so we do nothing and move to the next state and gets a call again from above. But the thing in 2.2 is this. Well, there's no such thing as negative acknowledgement packet. In fact, both positive, both negative acknowledgements are just ACK and carrying different sequence numbers. So this will also be a is ACK check. Okay? But the difference is going to be the sequence number they are expecting being different. So what should be the sequence number we expect here to pass so that we move on to the next state? We are expecting 0, right? So the sequence number here should be carrying 0. So we should be checking is ACK and particularly sequence number being 0. Therefore, we can move on. Send the next packet. If everything goes well, we should be getting another ACK packet, then carrying sequence number what? 1, because we just sent out packet 1, right? Now, the NAC here, check can no longer be valid and will be also doing the is ACK check. But what should be the matching sequence number here to trigger this action? Well, we just sent packet 0. If packet 0 was corrupted, the receiver would be what? Sending the last data packet received OK. So that should be what? Sequence number 1. Similarly, for the check here, it should also be is ACK, but sequence number what? 0. And that takes us to the sender side of the finite state machine. So we change this line as well as this line. So this line is what? Expecting 0, so check whether the sequence number equals 0. This is also now is ACK, and this should be carrying sequence number 1.